Okay, hello, my name is Professor Bayerlein. I'm the lecturer for the course Control System 2 this summer semester, and I think that you are signed in the control system in the Moodle course Control System 2. For this course, you need mainly this paper in Material Summer Semester 2020, the paper version 3.0. Open it and you can read it, and I will go in the next hours through this paper and tell you something of this. Also, the students of the German course Identifikation und digitale Reglersysteme also should go through this lecture. You see, you have the same paper opened and offered in your Kursmaterial Sommersemester 2020. Here you can find it and open it, and I will tell you something about this. So, if you open this paper, you can see this is valid for the semester, version 3, not only for ISE or MSOE students, but also for the German master course students. Just a quick view on the content of this lecture. It will start with chapter 6. So the Control System 1 course has as a content the chapters 1 to 5, and here you can see this is the following structure. So I start with chapter 6. For the German students, of course, this could be a little bit serious, but I think you can live with the fact that the first course, maybe you have not heard it. I will do some repetitions if necessary and tell you something about Control System 1 course in the content, during the content of this lecture. So, chapter 6, I want to start with digital PID controllers. The idea is, if we have designed an analog PID controller, there is a very simple method to convert it into a digital one. The background we want to discuss in this chapter. I will tell you something about the choice of sampling time, give you some hints how to improve your design of the PID controller, and finally I will present an example including simulation. In chapter 7, I want to show you that using the Z transformation helps in many ways to improve or optimize the PID behavior, but additionally, if we go through the design of digital filters, this also is helpful for your work as engineer. So this is also included in this chapter. So with this knowledge, you can design any filter type you want to have as a digital one, and very easy to program it. I show you how to program digital filters and controllers on any computing machine. Then the next part is identification of processes. I will show you some of the many existing ways to identify processes. The idea behind this is you need knowledge of the process before you can design a controller fitting to your process. So you need good knowledge about the dynamical behavior of a process. This is covered by some examples, and any example will be presented as a simulation program or a program module of my tool programs you can also download and run on your computer. Then chapter 9 is the last final chapter, which includes special version of digital controllers. if you have a computer, of course, then you have the possibility to introduce more complicated, more intelligent controllers like deadbeat controllers or predictive controllers we want to discuss. I want to introduce these ideas and show also the working of these special controllers with some examples. Okay, so far let's go into the first idea of digital controllers. You should know that the control loop consists, of course, of the analog process. Also, some people call this plant. So this is the problem we have to solve. Can we have constant temperature, or can we have a defined position of a system, or can we have design any physical value of maybe a module in your production line? The input is an analog signal, the output is an analog signal, and now see this dotted area. This is a replacement of an analog controller. You need just an intelligent machine, a programmable machine like a PC or an Atmel processor or a PIC processor or a PLC or any programmable intelligent, say, computer. But that is not all, but you need also two modules to connect the digital system with the analog system. For this you need a DAC, a digital to analog converter, including, of course, an hold block. This is no problem. And an analog to digital converter to read in the measured process output values into your system. Here you see a single loop system needs a set value, a reference value. This could be an analog one, but mostly this is a digital value, because then you can control the desired value with the computer, have nice human interfaces to set the desired value. The difference between measured output of the process and the desired value gives the control error, the control difference. This goes into the algorithm, and the algorithm calculates a control output value, which then is sent to the actuator input of your process. So the process includes sensor at the output and actuator at the input, and process behavior in the internal block here. So this block is the complete system, including sensor and actuator. Okay, the task of this lecture is I give you many different control algorithm possibilities, and we can discuss differences, advantages, disadvantages of several algorithms, so that you are able to program PID and any other controllers on a programmable machine. If you see the dotted line here, then this, in a little bit different drawing, can also be used as a digital filter. There is an analog input converted into a digital value. The algorithm converts an output value, and this is converted back into an analog value. The hardware, the digital filter, as you can see, is exactly the same as the hardware of a digital controller. Or in other words, a digital filter and a digital controller is really the same, but the application, the usage is different. If you use the digital filter in this way to control the output of a process, we call this controller. If we use this algorithm in this way, here is a signal and here is a filtered signal, then the same hardware works as a filter. Or in other words, we will see later, that we can use to design control algorithms. We can go into the theory of designing filters, can take tricks and ideas and methods of filter design used for controller design. So this is a very interesting fact. Note that here we have two arrows signed with TO or T-sub O or T0 or any expression is possible. This is a sampling time. Sampling time means that in a digital system you must work with samples, not with analog signals. The same is with digital filters. Digital filters samples the input signal with a sampling time T sub O and gives any T sub O a new output value. To show you what this means in the signals, look for the next page. There are 4 diagrams presented on this page. Let's have a quick look on these diagrams. On the top left side, this diagram is valued with x of t. Note for the letters I used in control systems, maybe this is different in some other literature. The output of a process is called, in my lecture, x. The desired value with w, the control difference with xd, the controller output with y, and the output held by the digital to analog converter y index h. Let's look back to my diagrams. This is the output of the process and this is a continuous curve, because the process is an analog process with measured analog continuous signal. Now, using my analog to digital converter, I only can sample values and convert into a digital number in a time distance. This difference between both times, this delta t, is our sampling time. So the analog curve now is sampled and you get now a series of digital values. These values are going into the computer, and the computer calculates with the control algorithm or with the filter algorithm, in any way calculates output values y of n. You see, n is the index if you have sampled values. And then the computer calculates here these values, and these values now are sent to the digital to analog converter, and the DAC makes from these values this curve, and this is an analog continuous curve. But you see the behavior of this curve is you have steps with constant areas and jumps, constant area, step, constant area, and so on, looking like a stair. So the typical output of a digital controller or filter is this type of curve. You can look at these type of curves in scopes if you sample with a scope the output of a digital system. Looks like this. Okay, some words to the comparison between analog and digital realization of a controller. The digital controller has some advantages. Let's look on this list. Maybe there are more than these points, but these are the main points. The first advantage is that the parameters of a controller, say K's and T's, in analog are realized with capacitors and resistors. And if you change the parameter, you have to change components. Here, if you change the parameter, of course, this is software. This is just the content of a variable. So it's very easy to change parameters of digital filters or controllers because these are just variables. Furthermore, if you have a computer, you can not only work as a controller, can as a multitasking system also offers a good human interface, like a graphical color display with touchscreen or anything else. Today are many human interface methods are possible. Again, with multitasking possibility, you can use one hardware for several actions. So maybe for slow controllers, it is very typical that one microprocessor controls, say, 10 to 20 independent temperature control systems with multitasking. Or other possibilities or other advantages is you can realize more complex controllers. Like you will see what a deadbeat controller is. It's only realizable in a digital version of a controller. There is no analog replacement of a deadbeat controller. Or you can work with fuzzy controllers or adaptive controllers. Adaptive means automatical change of parameters of the controller if the process parameters will be changed. Now you can use the controller to measure process parameters like identification, then make an automatic design of a controller. So adaptive controllers are rather comfortable if you don't want to design your own controllers. The computer can do this job for you. Or finally, you need a computer and digital controller if you want to have predictive functional controllers. You will see in chapter 9 there are some nice ideas, controller methods which are much better than a PID controller. But there are also some disadvantages. First, if you compare the price, I think there is no big difference. Today, a digital controller, look back to this first picture, a digital controller uses a microprocessor with ADDA converter, but this is available on one chip for some euros. So this is not really expensive. I think 30 years ago this was much more expensive, because then these parts are just very expensive compared with simple analog realization with operational amplifiers. But today the price is nearly the same if you do this analog or digital, but the development is more expensive. Note that in security and safe systems, a microprocessor has some problems, and then you have to find ways to make your hardware safe. Then this could be much more expensive than an analog realization. Then you have additional disadvantages like delay times. A computer needs some time to calculate, and the ADCs need some conversion times. This is added compared with analog ones. So this caused delay problems. And if you can remember in control system 1, a delay has a negative phase. Negative phase is not good for a closed loop system. Conversion problems and sample and hold caused delays. Then of course you have problems with sample times. What happens if your sampling time is too large? We will discuss this. So if the choice of the sampling time is not good, then the controller cannot run with good result. And of course then you have problems with amplitude discretion. That means your ADC is not accurate. It's depending on the numbers of bits used for conversion, and you get quantization errors. This caused noise in your system. Now this is just the list of disadvantages, but if you look into the realizations today of today's system, 99% of all controllers are realized as digital ones, so they want to have the advantages and can live with the disadvantages. So I think what we learn first is that our digital system is very interesting to discuss. We need some more information how these controllers works and how we can develop algorithms, and you see in this next step we will discuss how we can convert analog algorithms into digital ones, but this should be at this point the first part of this video. This video ends and the next point you can see in a new one. Goodbye until then.